Hey class, we've been taking a look at Unit C, measures of centrality and dispersion. We're finished with the first half of the unit, which is dealing with measures of centrality. Now we're going to take a look at measures of dispersion. Dispersion means spread, the spread of the data. And we'll be taking a look at two main measures and focusing primarily on the second one. I'll introduce also a couple of others that will just be briefly mentioned, but we won't do any calculations with them. So let's take a look at two families here. We'll call them X and Y, and they've got 9 kids. And these are the ages of the kids. So family X has a 3-year-old, a pair of twins, and an 8, 10, 11, 15, 17, and so on like that. So let's calculate the mean and the median for the ages of families X and Y. And so this is number 34 here. Let's take a look then at the mean. And I'll just put a little subscript here saying that this is the mean of the X's. So this will be the sum of the X's divided by n. And if we were to add all of these up, 3 plus 4 plus all the way up to 17, and then divide that by 8, there's 8 kids in each family, we'll get 72 divided by 8 is equal to 9. So the average age of the kids in family X is 9. Now let's take a look at the median of X is going to be equal to the value of rank 8 plus 1 divided by 2, right? 8 is our n, so that would be the 4.5 value. Now remember, that's not the median itself. We have to find out where that is. And so it's going to be 1, 2, 3, 4. It's going to be halfway between the 8 and the 9. The 8 and the 10, which makes it a 9. So the median then is equal to 9. So what we've got here is that the mean is equal to the median. These data are not skewed. All right, let's do the same now for family X. I'm going to change colors here. And family Y, pardon me. And so the mean for family Y will be the sum of the Y's divided by n. And if we add these guys up, 3 plus 7 plus all the way up to 17, divide that by 8, we'll get 9. So the same mean. And the median will also be equal to 9. So it's equal to the value, value of rank 4.5, which is 9. So it's right in here, halfway between these two values, 9 and 9, so that also is 9. So we've got the same means and the same medians for both X and Y. And yet, when you take a look at these two, would you say that the families are the same? Well, no, they've got the same kind of mean and median, but they're different. Now, the range here is something that we want to look at in terms of, well, how spread out are these families here? So the range is probably the most common measure that we tend to use in stats when you're talking to people who don't know about standard deviations, which is the better measure. And so range is something, of course, which you've learned about way back in elementary probably. And it's just simply found by taking the difference between the highest and the lowest values. So let's take a look then at family X and family Y. The lowest values are 3 in each case, and the upper values are 17 in each case. So let's just write that down. So the range then for family X is going to be equal to the highest minus the lowest is equal to 17 minus 3 is equal to 14. And the range for Y is equal to the same thing. And so what we have here is that the means are the same, the medians are the same, the range is the same. Does this really describe the differences between the spread of the two variables, though? When you take a look at these, And if I was to ask you which family looks more spread out, you would probably say family X is. So they both have the same range. They go from 3 to 17. But family X looks like it's more spread out than family Y. Of course, family Y has the quintuplets in there. But that's what most people would say, and actually you would be correct when we take a look at the interquartile range, at the standard deviation in a bit here. Just before we do that, just a couple of questions here, and that is, how would you calculate the range for grouped data? So let's take a look at an Excel spreadsheet here. And so here's our group data like this. Let's go to our frequencies there, like that. And so here's the ages of the people at the very top here. And how would you figure out the range here then of the group data? Well, probably there's probably two ways to do this. And one way would be to take the lowest class that has a non-zero frequency. So that would be the 10 to 19 here, has a frequency of 1. And then take a look at the highest frequency that has a non-zero frequency, and so that would be 90 to 100. And there's two possible ways that you could do it. You could take the difference of the class marks, so 94.5 minus 14.5 would give you 80 as a range. Or you could take the practical upper bound of the last class, which is 100, and the practical lower bound of the lowest class, which is 10. Now remember, we're not using this class here because it had a frequency of 0. So in that case, then you'd have 100 minus 10, which is 90. So that's how you would handle it. There's two possible ways here. Taking a look over here, now these all have frequencies which are non-zero. So the highest is 100. The lowest here is 30. So 100 minus 30 is 70. Or if you take a look at the difference between the class marks, it would be 94.5 minus 34.5, which is 60. Let's go back and just write that in here then. So there's two possible ways here, and that is the difference of the class marks of the highest class and the lowest class. Where neither have frequencies of 0. Okay. Or you could take, and this is probably the way that I would tend to do this more, is the difference here of the upper limit of the highest class minus the lower limit I suppose I should say and here, since I've already used the word difference, and the lowest limit of the lowest class where neither have frequencies of 0. And if they do, then of course you just simply go to the next one until you find a class with a frequency that is not 0. What are the problems with using the range as a measure of dispersion? Maybe stop the video at this point and think about that. I can think of two reasons. So the first reason here is that it only uses 2 points in its calculation. So it's the highest and the lowest point, and it ignores all the other ones in the middle here. Now, incidentally, that also is a problem with using doing a calculation of the median, is that once you've got all the numbers in order, it only looks at the middle number, or if there's an even number of values, the middle two numbers, and averages them out. So you're not using the values of the other numbers there. The second thing is that it only uses 2 points, and these are the extreme points. So think of the Bill Gates example again. And so Bill Gates has an income of $2 billion, and then somebody in the class made nothing last year, then we've got a range of 2 billion minus 0 is $2 billion. That's really not very indicative of the range of the marks, or the spread of the marks, right? It is, by definition, the range of the marks, but you've got a very extreme value in that case then. So what can you do about that? Well, there's a couple of things that you can do. Is you can knock off the ends. And so the interquartile range and the interdecile ranges do that. Now, what the interquartile range is let me just change colors here for a second. And if you had all of the numbers on a number line, think of a dot plot, and then you divided that into quarters. So you've got here 25% of your values here, and then you've got 25% here and 25% here. So a quarter in each. And they actually call these then Q1, Q2, Q3. Those are the quartile values here. I guess you'd call this Q4. And Q2 has another name for it, and of course it's the median. Right? It's got 50% of the values below it. So that's what we've got. Now, the interquartile range is the difference between the first and the third quartiles. So it's Q3 minus Q1. So it's the spread of the middle 50% of the values here. That's what that is. And I've got that written down here. The spread of let's write that again. The spread of the middle 50% of the values. Now, the other thing that you could do is you could divide them into, instead of quartiles, you could divide them into deciles. And with deciles, what you're doing here then is you're doing the same kind of thing here, but you're dividing it up into 10 different parts here. So this would be D1, D2, D3, D4, D5, D6, D7, D8, D9, and D10. So there's 10% in each of these. And the interdecile range is where you knock off the top and bottom 10%. So you would then take this here, right there, and you knock off the top 10%, the bottom 10%, and that way hopefully you get rid of the extreme values, the outliers. What you could do is you could divide it up into 20 groups and then knock off the top and bottom 5%. So that's a common thing, and that leaves you with 90%. But the interdecile range then gives you the middle 80% of the data, because what you do is you're knocking off the bottom 10% and the top 10%. So that's how you handle outliers. But we're going to move into something called the standard deviation. And it's the most common measure of spread when you're dealing with data. And the nice thing about it is that it uses all of the values in its calculation. So it says here in the discussion of the standard deviation, although the interquartile range eliminates the effects of the extreme values, it's still not the best measure to describe the spread of the data, because once the data is ordered, that's actually should say are ordered, because data is a plural word, it only uses 2 values in its calculation. The standard deviation is better because it uses all of the values in the distribution. I've got an aside here, and it says here, a general rule in stats and other mathematical disciplines is the more information that can be used in calculating some summary measure, the better. And for this reason, the standard deviation is a better measure of dispersion. By the same reasoning, the mean is considered to be a better measure of centrality than the median because it uses the magnitude of each other, the actual value, rather than just its rank or its location. The problem, of course, is that it is skewed with outliers. And again, think of the average income when you've got Bill Gates in your class. And so that's why the median is still a useful thing and we want to use it. But the mean gives you more information, and especially when the data are fairly symmetric, or you knock off those outliers and so on, it's actually a better measure of centrality. So similarly then with the standard deviation, is it's going to use every number in its calculation. Now, let's take a look at how we do that. So the standard deviation of ungrouped data is derived as follows here. We're going to choose some number that each value of x can be compared to. And an obvious choice to this is the mean, and this turns out to be best mathematically. So in other words, the mean is, in a sense, kind of the best representation of the data, single number that represents the data, because it's the middle of the data. It's the arithmetic middle of the data, right? Not necessarily the physical, but it's the arithmetic middle of the data. It's the balance point of the data. And so what we're going to do then is we're going to look at how each value of x differs or deviates from the mean. So we're going to come up with a new variable called not just x, but x minus mu. So I'm going to do that down here. Hey, before I do that, I just want to tell you a story here. So this is just an aside, but many years ago, when I actually first got out of high school and before I went into university, I worked with CN Rail, and I was working with a survey crew, and so I was low man on the totem pole. I was what they call a chainman, and so what we used to do then is when they went to set up a new subdivision or something, or in this particular case, it was looking at old railway tracks that they were trying to reinstate. Then they needed to go out and survey them and find out exactly where they were and where they were going and what the exact altitude was and so on. And when you think about it, actually, they used a similar method when we surveyed Canada a long time ago, like go back, 100 years ago. Further than that in the east, but particularly in the west when Alberta opened up in the early 1900s, then how did they set up different divisions and things like that and place a new town and so on? How did they know exactly where it was? Well, what they would do is somewhere over in the east, they found some rock, so you've got the Canadian Shield there and stuff, and actually I'm not sure where exactly they would have started, but let's say they started in Ontario and then they went both directions. And so they got some hunk of granite that wasn't going to be moving. And they figured out all sorts of methods here to figure out what's the exact longitude and the latitude and the altitude, using all sorts of different things like, barometers and different measures of the sun and so on, and finding out exactly where this particular thing is. Because remember, back then, they didn't have satellites. And so they couldn't just simply pull out a GPSR and find out the exact coordinates. And once they did that, they put in this spike, and they pounded it into the rock. And that thing was a benchmark. And so everything was measured from there. And then what they did was they would get a chainman to take this 100, in that case, yard, because we were in British imperial units, and so they would take this chain that was 100 yards long, and it was just simply a thin metal strip that kind of wound up like a tape measure, actually. and you'd stretch it out as long as you could, and then you get another guy. I suppose you could say, or a gal back then, but they didn't have many gals working on survey crews, so it was probably a guy. And so this guy would take a rod, so that was the rod man, and then they would figure out exactly where this particular chain was and what the altitude is, and they used a thing called a transit, and they found out exactly where this was, and they then moved the transit over to that point, and they continued on at 100 yards at a time. And they did that all across Canada until all of the populated areas of Canada was surveyed. And every once in a while, every few miles, they would stop and they would put in another big spike into like a granite rock or something like that. And that became a new benchmark, so that you didn't have to always start at the very beginning. You could go to the nearest benchmark. And if you actually walk down the street in Red Deer even, you can walk down the sidewalk in the downtown and so on like this, and every once in a while you'll see a little round brass cap, which is in the cement, and that's a benchmark. And you'll see that that's got survey information on it, and so they know the exact height, they know the exact altitude, they know the exact longitude and the exact latitude, and usually to about a cubic centimeter. So it's pretty accurate. Now, of course, nowadays they've got GPS, and that uses satellites, so you don't need to do that anymore, but they still have that system there in place. So those are the benchmarks, and everything is measured from the benchmark. Now, what does that have to do with standard deviations? Well, going back here, we use the mean as the benchmark of the data set. And so everything then is measured from the mean of the data. How much does each number deviate from the arithmetic center of the data? And that gives us a list of deviations. So let's go down here now to these data here. Now, it looks like it's in a table here, but this is actually just two columns here of ungrouped data. Right? I could write those out horizontally instead of vertically here, and it would look like ungrouped data. So I want you to just think of it as being ungrouped data. They're not put into classes. We don't have frequencies. They're just the 8 numbers. I'm going to start with family X, and I'm going to go this way to the left here. And so I'm going to come up with the first column here, which is a list of deviations. So how much does each number deviate from the mean? Well, we've figured out the mean. We've added these guys up here, and this comes to 72, and then we divided that by 8, and we ended up with a mu equal to 9. So the first number here would be 3 minus 9 is equal to minus 6. So what we have is that this number 3 is, its deviation is minus 6. It's 6 below the mean. 4 minus 9 is minus 5. And then we just keep going down, minus 5. And then we've got here minus 1, plus 1, plus 2, plus 6, and then plus 8. And if you were to add all of these up, you would end up with, well, hopefully here, 10, 16, yeah, 0. Which actually isn't a surprise, because remember that the mean is the arithmetic center, or balance point, if you like, of the data. And so all of the positive deviations must balance out or cancel out the negative deviations. So it would be nice, this is actually a nice method, because it's showing how each number deviates or differs from the mean. And so it's a good measure of spread. And so logically, it would be good to find out what is the average of those deviations. And so the average, of course, would be found by, so the average deviation would be found by summing up all of those deviations and dividing through by n. Problem is that it always turns out to be 0, because, of course, the mean is the arithmetic center point. So it's a good idea, though, And so how do you get around that problem of the positives and the negatives canceling each other out? And there's two possible ways of doing that. One is to just change them to absolute values. And so if you just ignore all of the negative signs and make them all absolute values, make them all positives, then you could calculate out the average of the absolute deviations of the means. The other way to do them is to square them, because if you square a negative number, then it turns into a positive number. And that actually is the way that statisticians do that. And there's reasons for that, which I'm not going to go into. There's properties of estimators, and we would say that this is a best linear, unbiased estimator, and that's something which is beyond what we're doing in this particular course here. So you're just going to have to take my word for it that the statisticians have found that the better way of handling this then is, instead of taking the absolute deviations, we take the squared deviations. So we take this minus 6 here then, and we square it, and that will give us a plus 36, right? All of them will be positive. Minus 5 squared is 25. 25, 1, 1, 4, 36, and 64. And that sums up to, I'm going to turn to the right page here, I guess. I think it's 192. Yeah, it's 192. So then what we can do is we can take the average of those. And that's something, the average of the squared deviations from the mean is something called the variance. And it has a special symbol called sigma squared. Now, you've seen a capital sigma, that's a capital sigma, but this is a small sigma. There's no relationship between the two, by the way, because you use sigmas adding stuff up in all sorts of things, like calculating means, right? But that's just the symbol that they use, and they call it sigma squared. So sigma then is the, what is it, 17th, 18th letter of the Greek alphabet. And whenever you see a Greek symbol, like a mu, or in this case now a sigma squared, then that typically means that you're dealing with populations. And so here's sigma squared, and here's n. Capital N, of course, means the number in the population. And so the variance is the average. And remember, an average is just when you, whoops, that's not what I want. An average is when you sum something up and you divide through by n. The average of the squared, here's your squared, deviations from the mean. That's what these guys are right here, mu, x minus mu. So that's what a variance is. The problem is that that's still a squared value. And so the last thing that we do then is we take the square root of this guy, and we come up with something called the standard deviation. Now, if you were to explain what a standard deviation is, I guess the closest you would come to is to say it's kind of like the average amount that each number differs from the mean. That's actually not what it is exactly. I mean, that's actually what if you were to average out the absolute values, the absolute deviations from the mean, that's exactly what you would get. But it's a similar in concept if you're explaining this to somebody who doesn't know stats. It is important to note that the above formula here is for population data only. If we're talking about sample, if it says in the problem that we've taken a sample, then we use a slightly different formula here. Instead of sigma, we use S. So instead of sigma squared for the variance, the sample variance would be S squared. And instead of using mu, we would use x bar. And instead of using n, we use Oh, n minus 1. That's interesting. So it's not just replacing the symbols like this. It actually uses n minus 1. And at this point, I'm not going to talk about why we would use n minus 1. It's something, again, which is a better estimator. It has something to do with, when we get later in the course, something called degrees of freedom. And at this point, I just want you to take it as it's a it's a measure. It's an allowance, if you like, for more uncertainty, because variance is a measure of uncertainty when we get into inference. So just take it as a given at this particular point here, but you have to use n minus 1. If you take the square root of that, then you end up with this guy down here. So those are the formulas that you need for that. By the way, as we're going through Unit C here, what I'd like you to note is that at the very back of your book, you're going to find that there's a formula sheet which you can use for your exam, and it's now got all of these formulas that we're going through here. So right back to Sturgis method in Unit G, and right through Unit C here. So it's important that you take a look at that. So let's take a look here then at consider families X and Y to be two separate populations. And so what we're going to do is we're going to come up with the variance of each one. Now, they're going to be considered to be populations, because that's all we're interested in. And so we're going to be using sigma squared, not s squared. So let's calculate now. We're going to have, for family X, I'll put a little x down here just to show that it's x. It will be the sum of the x minus mu's squared divided by n. Now, we have already calculated up here. This number right here is the numerator. That's the sum of the x minus mu's squared. And then we just need to divide through by n, which is 8. There's 8 numbers. And so we're going to say that that's 192. Divide that by 8, and that gives us 24. So the variance is 24. And then the last thing that we're going to do here then is we're going to take the square root of that. So the standard deviation is equal to the square root of 24, which is about 4.90. All right, now let's do the same for y. And this is where I'd ask you to stop the video and then go and fill in the numbers here for the y column. The y column's over here. Okay, I'm going to assume that you've done that and that you've calculated. And let's go through and do the same kind of method here. So I'm going to take the y minus the mu's. Now we have to figure out what the mu of the y's is. We've already done that earlier in this unit. Is this actually summed up to 72 divided by 8? We ended up with the same mean of 9. All right, and so 3 minus 9 is equal to minus 6, and then 7 minus 9 is minus 2. 9 minus 9 is 0, 0, 0, 0, 0, and this is plus 8. And of course, if you add those all up, the average of the deviations is equal to 0. So no surprise there. It'll always happen that way. But we're going to square them. So let's take minus 36 and square that. We'll get 36. Minus 2 squared is 4. 0 squared is 0. And 8 squared is 64. Add those up and you get 104. All right, let's go back to where we were then. And we'll have here then that the variance of the y's will be equal to the sum of the y minus the mu's squared over n, which is 104, over 8, which is 13. And the standard deviation of the y's will be the square root of 13, which is about 3.61. So what we can say is, according to the standard deviations, we can see that family X actually does have a greater spread than does family Y, which is what we intuitively found when we took a look at the numbers before. So they've got the same range, they've even got the same mean and the same median, but we would say that X is spread out more, and according to the standard deviation, it is. Now, before we conclude this here, I want to just go through here a couple more things, and that is that this is an okay method to use when you only have about 8 numbers and you can come up with these particular columns right here. So that works out quite well. But what happens if you had, say, 50 numbers, like the ages of our 50 people? That's really a pain, because you'd have to subtract off the mean, and the mean in that case was 70, from each number to come up with a deviation, and then square each of those, and then average them out. Whew, that would take a long time to do that. Is there an easier way to do that? Well, there is, and it's using these formulas right here. So these are algebraically equivalent formulas to the ones above. So we call these the computational formulas for the variances. And the standard deviations, of course, is just the square root of those. So this is for the population, and then this guy here would be for the sample. And if you're good at algebra, you can just simply actually take this original formula up here for the variance and just this guy here, and then you can use a little bit of algebra and see what you come up with. And you should come up with exactly the same thing. I would not ask you to do that on an exam, by the way. All right, so let's take a look then at the ages of X and Y to be population data. We're going to fill in another couple of columns 1 and 8, and we're going to use the computational formulas up here. So this guy right here. Oops. Oh, it disappeared, sorry. That guy up there. And we will get to this guy later, but right now we're going to take a look at this guy right here. So let's go up here, and I'll change colors here. Let's go with a blue. So I'm going to come up with a column here, which is just the X squares, and we'll have another one over here, which is just the Y squares. And really, first of all, you never have to use this column here. That's just an educational kind of thing that shows you that the average of the deviations always turns out to be 0. And in fact, you don't have to use this column either. You can, if you've got a small data set like this one, then you can certainly do that. But what you typically would do is jump straight from here to that column here and just ignore the other ones like that. So what you do then is you take 3 and you square it and you get 9. 4 squared is 16, and all the way down. 16, 64, 10 squared is 100, 11 squared is 121, 15 squared is 225, 17 squared is, I don't know, is it 349? Let me check my notes on that one. It's 289. There we go. And then you add those together and you get 840. Now while we're here, let's do the same over here. So 3 squared is 9, 7 squared is 49, and then 9 squared is 81, and we've got 5 of those. And then 17 squared is 289, and that's going to sum up to 752. So keep those two numbers in mind. The 840 for the x squares and 752 for the y squares. And we're going to come down here then and use the computational formulas here and say that the variance of the x's using the computational formula is like that. And so that's going to be 840 divided by 8 minus 9 squared. And that comes to 24. And then, of course, sigma is equal to the square root of 24, which is 4.90, as before. And then let's do the same for the y's here. So the sum of the y squares over n minus the mean of the y's. The mean is not over n. It's outside. And that comes to 752 over 8 minus, it also had a mean of 9. And that comes to 13. So there we go. Sigma is equal to the square root of 13, which is 3.61, right? This is for the x's, this is for the y's. There you go. Now, let's actually just finish these two off here. Consider the ages of the 50 people. And I would assign this for homework, but there's 50 numbers, so let's just walk through them here. And so I'm going to use the computational formula that goes like this. Sigma squared is equal to the sum of the x squares over n minus mu squared. And so what we do then is we square each number. 14 squared plus 21 squared plus 32 squared all the way up to 97 squared. That whole thing is divided through by 50, and then we subtract off the mean, which is 70 squared. All right. So that's what we've got here. Now that mean came from page C3, I believe it was. Where's page C3? It's about page 69, somewhere around here, I think. Yeah, here it is. Okay, so there's the 70 right there. And then, I should have paid attention to which page I was on. There we go. Sorry about that. Okay. And this whole thing then comes to, let's see. Let's do it down here. The numerator is 260,208 over 50 minus 70 squared. And that comes to 304.16. And then finally, the standard deviation will be the square root of that, which is 17.44. So again, this is not an exact definition, but it kind of means that on average each number differs from the mean of 70 by about 17.44. All right, let's go and do the same for the marks of 50 students. And here then, it says, I want you to consider these to be sample data. And so in that particular case then, back where we were on page C3, marks for the 50 students, we had the mean equal to 60. If these were considered to be sample data, what we would do then is we would say, well, x bar would be equal to the sum of the x's over little n, which is exactly the same formula. So when you're calculating means, you use exactly the same numbers, and you just use different symbols, but it's the same formula here. So the mean would turn out to be 60 in this particular case then. Okay? So let's take a look down here then at the marks for the 50 people here. And so we ended up with an x bar equal to 60, and that was from page C4. Page C4, although we calculated that as population before, but sample would turn out to be the same. And so then we would have s squared is equal to, and this formula is a little goofier, and so it's a little more complex. Let's take a look at it here. So it's this guy right here. And so it's the sum of the x squares minus n times x bar squared, and then the whole thing is divided by n minus 1. So the way that you do that then is you take every number and square it. 34 squared plus 41 squared plus all the way up to 90 squared. I'm going to put that in brackets there. Minus n, which is 50, right? That would be our n, times 60 squared. That was our x bar. And that's all over 49. So 50 minus 1, which is n minus 1. And that comes to 146. Whoops. There we go. 146.94. And if we take the square root of that, we'll get 12.12. By the way, if you calculate this using this is a population, so using this formula up here, you'll end up with a standard deviation of exactly 12. That's the way I designed the data. This is a perfectly normal distribution with a mean equal to 60 and a standard deviation of 12. But we're handling that as a sample, so that's what we end up with. Number 44, can the standard deviation be calculated for nominal data, such as the genders of fossa members? And the answer is no. So with nominal data, the answer is no. And you want to think of it the same argument that we had with averages. Remember, in order to calculate a standard deviation, you need to be looking at deviations from the mean. And so when you're talking about nominal classifications here, remember any numbers that you assign are just simply used for classification purposes. And you don't even have to assign numbers. And so you can't then come up with an average gender, just as you can't come up with, and therefore you can't come up with a standard deviation of a gender. So you can't do that for nominal data. Ordinal data is, the answer is meh. And so remember the argument that we had for calculating a mean for ordinal data. So what's the average movie rating, say on IMDb? And you can come up with a particular rating here, but you don't want to take it more than one decimal places. So for instance, with IMDb ratings, they'll say this movie is rated as a 6.6 or something. And that's because we don't know the differences between the numbers, and my 6 is different from your 6, and all that kind of stuff. And so you can only do it really for ordinal data. So you could calculate it here, but you have to take it with a grain of salt. For interval data, the answer is absolutely, that's what it's made for. And of course, interval includes ratio data. So that's what we've got there. And that brings us to the end of that. Next, we'll take a look at the standard deviation of group data. So I'll end the lesson here.